Hello, and welcome to the OpenBrIM platform.
In this video, we give the assistant only a performance objective, without describing the solution method. Run the analysis, and report the maximum deflection at each construction stage. If the final stage displacement exceeds 5 inches, increase the girder depth iteratively until it is reduced to an acceptable level. The critical point here is that the task defines the objective rather than the result. We do not tell it to assign a specific value. We provide a boundary condition and expect the assistant to determine the steps itself. The work is carried out on the steel eye girder training example model. The assistant first initiates the finite element analysis itself. When the analysis is complete, it automatically retrieves the results, extracts the maximum vertical deflection at each construction stage, and compares it against the 5-inch condition. The final stage deflection is calculated as 10.11 inches. Since this exceeds the limit, the assistant initiates the iterative improvement on its own. In the first iteration, it increases the web depth from 60 inches to 84 inches. Because increasing the web depth is the most direct method of reducing deflection by raising the flexural stiffness. It verifies that the change has been applied and repeats the analysis. The most important point is here. With an 84-inch web depth, the deflection drops to 5.45 inches, very close to the limit, but still above it. Rather than guessing blindly, the assistant evaluates the stiffness trend between the two iterations and, by extrapolating this trend, predicts that a 90-inch web depth would reduce the deflection to approximately 4.8 inches. In other words, it anticipates the next step and selects the value that will reach the objective directly. In the second iteration, it increases the web depth to 90 inches and repeats the analysis, and the result confirms its prediction. The deflection drops to 4.81 inches, and the condition is satisfied. The assistant thus reaches the objective in 2 steps, reducing the final deflection from 10.11 inches to 4.81 inches. What stands out is that the process is not a trial and error loop. The assistant interprets the results using engineering logic, uses the stiffness-deflection relationship to anticipate the next step, and avoids unnecessary iteration. This demonstrates that the system does not merely run commands. When given a performance objective, it can produce its own design decisions. This example shows how the assistant can move from a single performance target to a verified design solution without step-by-step instructions, relying entirely on engineering logic to guide each iteration.